Optogenetics is a relatively new field of neuroscience that involves gene therapies applied to animal models that creates light sensitivity in the function of specific neuronal circuits in the brain. And specifically, it allows you to use exposure to light to control behavioral responses and to untangle complex neuronal circuits by specifically targeting, turning on and off specific classes of cells within the brain. Strategic implementations of these optogenetic ideas allow one to tease out the behavior of the brain, especially conducted with these kinds of technologies that can lead to insights into Alzheimer's disease, Parkinson's disease. For an application like optogenetics or other investigations of the brain, you'd like to be able to deliver that electronics down into the depth of the brain. And the question is, how do you do that? And we think we've come up with some strategies that allow some powerful capabilities in that realm that involve ultra miniaturized devices, very thin flexible geometries that can be delivered down into the brain or into other organs. So this is one of the devices that we have built. So the actual devices and all of the active components are at the very tip of this thin filamentary structure. It's small enough to fit through the eye of a needle, for example. This entire system mounts on a miniaturized needle device with a dissolvable biocompatible adhesive. So you can use the needle to inject these devices down into the brain. The adhesive dissolves away and you simply remove the needle, leaving behind classes of very advanced optoelectronic systems that have cellular scale dimensions. So this is where all of the active components are located. They're connected via very tiny wires to this power module, which mounts on the outside of the animal. And it consists of an antenna and a rectifier circuit that allows you to deliver power to the device using RF energy, similar to energy that comes out of your cell phone. This device harvests that energy and then delivers it down to turn on and off the electronics and the LEDs that are located at the tip end of this device down into the depth of the brain. So the antenna allows the animal to move freely within its cage or within the space of a room. The releasable plug can allow disassembly of the overall system so that the animals only need to accommodate this part of the device when experimentation is not underway. So the LEDs that we typically use are blue in color. That activates this light responsive region of the brain to induce the release of dopamine. So it creates a pleasurable response in the animal. And the release of that dopamine then can be used in a training process to create desired behavioral responses in the animal without any kind of physical reward, just a reward induced by this light-activated release of dopamine in the targeted cells. And then I think longer term there is some potential for these techniques to be used in a therapeutic manner. So the gene therapy approaches that are used to create this photoresponsivity in animal models are not too different than the gene therapy approaches that are being used in early clinical trials with humans. So I think there's a longer term potential for direct impact on human health in the therapeutic sense, but certainly the immediate opportunities are in fundamental studies of neuroscience.